This Argo ocean float works because its physical volume shifts while total mass remains fixed. The clever bit here is moving hydraulic fluid into an external bladder. An internal hydraulic pump forces fluid into an external rubber bladder on top of the pressure housing. Expanding this external bladder displaces extra seawater without adding any physical mass to the overall robot. Lowering overall density allows the instrument to rise smoothly through deep water to reach the surface. However, simply pumping hydraulic oil into an external bladder is not as straightforward as it sounds when battling turbulent surface ocean waters. Early engineering models assumed that simple fluid retraction would immediately initiate a smooth, steady downward dive directly from the sea surface without any additional control mechanisms. In reality, strong surface wave turbulence and warming thermal boundary layers temporarily store the float's initial descent if its volume displacement is even slightly mismatched. If the internal hydraulic reservoir withdraws too little oil, the float remains overly buoyant and drifts aimlessly on rough surface currents without diving deeper. Without precise volume control during initial submergence, early oceanic float prototypes struggled to break through complex surface wave dynamics and buoyant water stratification. Engineers resolved this initial obstacle by implementing precise stepwise hydraulic valve timing and metered oil retraction inside the main pressure housing. The high-precision hydraulic pump draws an exact calibrated volume of synthetic oil from the external rubber bladder back into the internal storage reservoir. By deflating the external bladder completely, the overall displaceable volume of the float drops significantly while the total physical mass stays completely unchanged. This subtle increase in overall float density overcomes surface wave action and warm thermal stratification, allowing the float to submerge reliably through the upper ocean. Once safely submerged past the turbulent surface zone, the float smoothly descends to its target parking depth of roughly 1,000 meters below the surface. At this intermediate 1,000-meter parking depth, the ocean robot drifts neutrally with deep ocean currents for several days, without consuming any motor power. The bigger problem was descending even deeper to 2,000 meters, where massive hydrostatic pressure crushes flexible components and resists internal pumping. At a depth of 2 kilometers, surrounding ocean pressure exceeds 200 atmospheres, pushing relentlessly inward against every exterior mechanical seal and flexible bladder. It appeared nearly impossible to pump hydraulic fluid outward into an external bladder against thousands of pounds per square inch of deep ocean water pressure.
A standard electric hydraulic motor would stall instantly under such immense mechanical resistance, or completely drain its internal battery supply attempting a single bladder expansion. Furthermore, extreme hydrostatic pressure slightly compresses the solid aluminium hull, making the entire float slightly smaller and denser as it sinks deeper into the abyss. If the float becomes significantly denser than the surrounding seawater at extreme depths, it risks sinking uncontrollably all the way to the abyssal seafloor. To survive these extreme physical forces and descend back upward safely, the float required an exceptionally efficient high-pressure buoyancy engine capable of extreme work. To overcome crushing deep-sea pressure, engineers designed a specialized high-pressure hydraulic displacement system safely housed within a thick-walled, high-strength aluminium pressure cylinder. The internal buoyancy engine couples a compact electric motor to a high-efficiency positive displacement hydraulic pump capable of generating immense output fluid pressure. When the standard 10-day drift period at 1,000 meters finishes, the float activates its internal hydraulic valve system to descend further down to 2,000 meters. Upon reaching its 2,000-meter deep profile depth, the internal hydraulic pump reverses fluid flow, driving synthetic oil outward into the external flexible bladder. Pumping oil into the external bladder against 200 atmospheres requires immense mechanical torque, managed by precise internal valve timing and heavy-duty hydraulic lines. As the external flexible bladder gradually inflates on top of the housing, the total physical volume of the cylindrical float expands by several hundred cubic centimeters. Because the mass of the sealed aluminium float remains strictly constant, increasing total displaceable volume causes the overall bulk density of the robot to drop significantly. When the float's bulk density drops below the density of the surrounding deep ocean water, positive buoyant force accelerates the instrument smoothly upward towards the surface. As the robot ascends through the 2-kilometer ocean column, high-precision scientific sensors continually gather critical temperature and salinity measurements along its vertical path. Sensors mounted at the top of the pressure hull continually record fine-scale temperature profiles from deep abyssal ocean water all the way up to the surface. Simultaneously, specialized electrical conductivity sensors measure seawater salinity profiles across varying vertical depth strata throughout the complete ascent, recording subtle variations in ocean chemistry. Upon breaching the sea surface, the external bladder remains fully inflated to provide maximum positive buoyancy and stability during critical satellite communication sessions. An integrated satellite antenna at the top of the casing transmits collected profile data directly to orbiting satellite networks within a concise, energy-efficient surface window. After data transmission completes successfully, the hydraulic pump retracts the oil back into the internal reservoir, preparing the float for its next 10-day drifting cycle. This fully autonomous buoyancy cycle enables thousands of global ocean floats to gather long-term climate and oceanographic profile data for years without any human physical intervention. Do not encourage viewers to recover, open, obstruct, or interfere with scientific floats. Any found instrument should be handled only under guidance from the responsible program or relevant maritime authority. By precisely controlling physical volume through internal hydraulic fluid displacement, the Argo float masters extreme ocean pressure variation across 2 full vertical kilometres. This elegant mechanical strategy eliminates heavy thrusters, relying entirely on variable density to navigate deep ocean currents reliably across entire planetary ocean basins. With every vertical profile cycle, these autonomous ocean robots construct a comprehensive, real-time, 3-dimensional map of Earth's hidden thermal and salinity dynamics. Mastering density control through fluid displacement turns an isolated mechanical cylinder into one of modern climate science's most powerful planetary ocean monitoring systems.